surface. So the crew lands in vicinity of the ascent vehicle, in their habitat vehicle, where they can then recondition themselves to start the exploration strategy. And they explore Mars for about 500 days, transfer to the other vehicle, ascend to Mars orbit, where they've rendezvoused with that transfer vehicle that's been waiting in Mars orbit while they're exploring the surface. And then again, 180-day transits back to Earth for direct Earth entry at the end of the mission, 30 months later. So total mission duration for the crew is about 30 months long, which is a significant period of time. So if you take that general mission approach, and that's, again, design reference architecture, it's built upon the foundation of a lot of other studies. And you see up here in the next chart, some of the key challenges that we have found and we continue to find through these architecture studies of what are some of the key things that are required from a human exploration of Mars perspective. Heavy lift, we see as one of those critical elements. So the SLS that Charlie talked about, evolving to a capability of about 130 tons will enable this type of an architecture. Each time, even when we dial in all those technologies, Charlie talked about it, if we went with today's technologies, it would be 8 to 12 times the mass of what we think today in terms of space station. Even dialing in all those technologies, it's going to be about 2 to 3 times a mass of space station every time we send a crew to Mars. So heavy lift and being able to have robust heavy lift capability is really one of those enabling elements. But that's also large volume. Being able to launch large volumes is also key. I talked about entry, descent, and landing. Today, our capability is limited to about 1 metric ton of landed capability, landed payload on Mars. To do this type of approach, we're going to have to get to at least 20 tons. Our preferred approach is to get to about 40 tons of landed mass, or usable mass on the surface of Mars. So entry, descent, and landing, new technologies and new techniques to serve that is really critical. Human health and performance, I'm not going to talk too much about that. Dr. John Charles will discuss that in a minute to go into some of the details. And you also hear some more discussion on that in panel 3 later in this conference. Cryogenic propulsion, concepts like oxygen, methane type of engines, again, compatible with the in-situ resources that we want to produce on Mars are critical. So throttleability, long life reliability system. Being able to extract oxygen out of the atmosphere, we found that to be very, very useful from a total leverage and total exploration architecture enabling capability. So extracting oxygen out of the atmosphere is key. Advanced in-space propulsion is key. Ben Donahue will talk about that a little bit more. Within the agency, yeah, we're rocket fire and smoke type of people because it's key for these exploration architectures. Really maximizing our propulsion capabilities, launch vehicle capabilities is important. But right now we have various different concepts still in play that we're continuing to look at. Advanced chemical propulsion, nuclear thermal, nuclear electric. The question came up about VASMIR, the VASMIR engine. We're continuing to investigate it. It is electric propulsion type concept, nuclear electric. So we're continuing to investigate it in terms of its capabilities and use. And if we have time, we can go into a little bit more in terms of that technology in the question and answer session if we need to. Reliability and maintainability is another one of those key challenges. As we talked about, no matter how you slice it and dice it, human missions to Mars are 18 to 30 months long. And so having the capability to have reliable systems, being able to repair systems, the crew is not going to have anytime logistics. As you see, the opportunities going to Mars are very limited. So the crew needs to take all their capabilities and systems with them to be able to repair things should they break. So advanced logistics and reliability and maintainability are important. Cryogenic fluid management, consistent with that advanced propulsion concept, is important. Being able to store oxygen, hydrogen, methane, perhaps xenon, things like that for long periods of time, 900, 1,200 days in space with as low a boil off as we can is important. Advanced operations, new concepts of the human exploration of Mars will require us to look at the problem differently. We're not going to be able to see every bit of data real time coming down from these missions. We're going to have communications delays that we're going to have to deal with. We are not going to have anytime logistics, as I mentioned earlier. So once the crew gets out, few days out from Earth, they're committed Surface power, Mars is kind of a harsh environment, and so advanced in-space propulsion. Right now our concept is a nuclear fission reactor, about 30 kilowatts total power, consistent with what we need for ISRU producing the propellants, but also while the crew is there is critical. So advanced power, keeping the crew healthy and maintaining them. Science, we're there to explore. So providing exploration mobility, where we land is going to be in a safe location. We're not going to land in a very dangerous location. Generally those safe locations aren't necessarily geologically interesting right at the location. So enabling the crew to be able to do long-range exploration and explore the geologically interesting sites is going to be key. And Dr. Beatty will talk about that a little bit more in his discussion about Mars and what we have today. And when you look at that, as Charlie talked about, that's in the grand scheme, that's a lot to bite off in one chunk. And so we don't view the strategy as straight to Mars, but it's an incremental approach. And you look at all those technologies that are required from a human exploration of Mars perspective, and you map. What we're doing is we map those back to other destinations and say, okay, which technologies are required for the various destinations, and which of those technologies make most sense to demonstrate and prove some of their capabilities. So you'll see within near Earth space, for instance, space stations, a lot we can learn in terms of the human health and performance, a lot of the operational aspects of maintaining systems for long periods of time, a lot of those gravity phenomenon type of issues. We'll talk about that as the conference goes on. But it's an incremental approach as we're looking at it. And this is another slice of how you can look at it, which Charlie talked about. The path that we go to Mars is still evolving. This is a snapshot of what came out of the Human Exploration Framework team late last fall. And it's an incremental approach, looking at various different destinations. What we might do in low Earth orbit, what we might do in high Earth orbit, like geostationary orbit, repairing satellites, things like that. How lunar missions fit in terms of proving some of our capabilities and systems. All about perhaps near Earth objects. Exploring asteroids can serve as a good vital test run of an eventual Mars mission. So it's an incremental approach as we look at the systems and understand their capabilities in order to tie this framework together. So we don't just focus on necessarily on one destination by itself, but really understand how all the destinations drive some fundamental key capabilities that all work together to establish and achieve our goals as we go along. If you look at another way of slicing that, if you look at it from a human health and an exploration perspective of Moon versus Mars, we want to get to the planetary surface. So there are some common capabilities and needs as you look across that spectrum. The Moon can serve as a good formulation in terms of really understanding the surface operations, testing the operational procedures, understanding human health and reduced gravity in a 1/6 gravity environment as an analog for Mars missions. Proving a lot of our systems and capabilities. Near-Earth asteroids, on the other hand, can serve as that test bed for a lot of in-space transportation elements. Getting crews to remote distances as quickly as we can, exploring those destinations and getting them back. So the transportation elements, the in-space habitation systems, life support, those sorts of things. There's a common intersection in the middle between those where we need some capabilities that are common between all those destinations. Heavy lift, in order, efficient, robust capability of launching systems in space, getting crews to low Earth orbit to start those missions off, and then at the end of the mission, high-speed return, to return the crew back to Earth. And if you do things right, and think systematically of how Moon can play in those lunar